Thermal analysis of a monolithic microwave integrated circuit, or MMIC, will be demonstrated for this compact two-stage X-band power amplifier as described in a paper by Klockenhoff et al. In 2006. We will use the non-proprietary generic FET template as our starting point, but custom templates designed for a particular technology might be more appropriate for proprietary MMIC analysis. We'll begin by reconfiguring the device to model GaN on silicon carbide technology. So we'll change the substrate material to silicon carbide and the epilayer material to gallium nitride. Epilayer 1, which will represent the nucleation layer, will be aluminum nitride. Now we'll set the thicknesses of the epilayers. The nucleation layer will be 0.1 microns thick. The buffer layer will be 2.3 microns. And the barrier and cap layers together will be 27 nanometers. Next, we want to fill in the source pad vias. So we'll go to the components list and we'll select the source pad via hole and change that material to silicon carbide, and the source pad via metal to silicon carbide as well. We're basically going to eliminate the source pad from the device, and we'll do that by setting the source pad length down to some small value, in this case 5 microns. Now we'll thin down the gate bus width and the drain bus width to 20 microns. Next, we want to set the channel dimensions. We'll set the finger width to 125 microns, the gate to drain distance to 2.1 microns, the gate length to 0.4 microns, and the gate to source distance to 1 micron. To set the gate-to-gate spacing, we'll specify the source and drain lengths. We'll set all the source lengths to 49 microns and all the drain lengths to 49 microns. Finally, we'll set the number of gates. The number of gates in the driver stage FET for our MMIC is 12, but we're modeling half a device here, so we'll put in 6. And that's our driver stage FET, so we'll save that as stage 1 FET. Next, what we want to do is create a layout. So we select create layout from the file menu and then type in a title for our layout, two-stage X-band amplifier. The length of our MMIC will be about 3,800 microns and the width 2,500 microns. Then we'll set the positions of the stage 1 transistor at 660 microns in X, 750 microns in Y. We'll mirror the device, which says we want to include the full 12 gates of the device in the MMIC, and then we'll rotate it by 90 degrees counterclockwise. So there is our driver stage FET positioned on our die. So we'll save this layout as X-band amp. And now what we want to do is configure our stage 2 devices, and they're very similar to the stage 1 devices. So I'm just going to open the stage 1 FET and use this as a starting point. And basically they have half the gate-to-gate spacing and twice the number of gates. So I'm going to set the source lengths all to 24 microns and the drain lengths all to 24 microns. and the number of gates to 12. So that's our power stage FET, and we'll just save that as stage 2 FET. Now we want to add the power stage FETs to our layout. So let's open our layout and select Edit Layout, and then we'll add stage 2 FET, and we'll position the first one at 2,150 microns in X and 220 microns in Y. And we'll position the second one at the same X position but shifted in Y to 1,310 microns. So there's our full X-band amplifier model, and we'll save that. Now all we need to do is set the power levels. So if this device is dissipating 2 watts per millimeter in the driver stage, and then for each of the power stage it's dissipating 4 watts per millimeter, we can just enter those values, and then we would say run simulation, and we would get our solution. I'm going to load in the solution that I've already computed, because the simulation takes about 2 hours on my machine. It uses over 8 gigabytes of memory, and it takes quite a while to run. It has 1.2 million nodes in the solution, so it's a pretty big finite element problem. So I'll just load in the solution that I've already computed and display it. I can turn on the template wireframe to show where the devices are. So here's the driver stage FET, and here are the 2 power stage FETs. And to get a better idea of the peak temperature distribution, what I can do is plot the max temperature over the device, over the whole MMIC, and what you see is the driver stage FET is relatively cool, but the power stage FETs are very hot. And if I want the details of what the temperatures are on each device, what I can do is ask for a snapshot and type in a file name for the snapshot. And what comes up is a window which shows me all the details of my simulation, including the temperatures on all the components in each device. And the details of the snapshot can be found in the user's manual, so I won't go through them here. But that basically completes the thermal analysis